Okay, so we're going to be looking at these different problems to help us decide like what's going on. So this first problem, look at how the partial sum is changing and decide if it's going towards a singular number or not. So does the following series converge or diverge? So I'm going to fix one thing on here is we're going to add it going on towards infinity. So we're going to add a plus dot dot dot. And we're going to do this by looking at these partial sums. So we're going to look at these different partial sums to see if we can find a pattern. So S sub 1 is the first term in our series. This is 1. So S sub 1 is 1, and we're done. S sub 2, we're going to look at those first two terms. So we have 1 minus 2. 1 minus 2 is negative 1. So our first sum is 1. Our second sum is negative 1. S sub 3. So we have 1, 2, and 3. So we have 1 minus 2 plus 3. 1 minus 2 is negative 1. We add 3 to it. We're going to get positive 2. So right now, so far, I see we have a sum of positive 1, then a sum of negative 1, then a sum of positive 2. S sub 4, we're looking at the first four terms, 1 minus 2 plus 3 minus 4. Well, 1 minus 2 plus 3 is 2. If we subtract 4 from that, it's going to give us negative 2. And then I'm going to add in these last two. We have S sub 5, which is the first 5 terms. If I add these all together, this gives me 3. And if we find the sixth, which would be adding that in, we're going to notice that it gets to negative 3. So when we're looking at this, we're looking at these different sums. So as the limit, as n approaches infinity of S sub n, if we look at what's happening, we're kind of bouncing back and forward from a positive number to a negative number. And not only that, but that positive and negative number are getting bigger. So if we were to think about this as like a graph, where this is n and this is the value of S sub n, we're starting at 1, then we go to negative 1, 2, negative 2, 3, negative 3, and it's going to keep doing kind of this. So as we look at this, there's not going to be a singular number that we get to. So S sub n, as we look at the limit, is not approaching a singular number. So the series diverges. So because we don't approach a very specific number like we did with 1, and it's kind of going back and forward, it's getting bigger infinitely, we're going to diverge. Okay. So, given the sequence 1/2, 1/4, 1/8, 1/16, write an expression for a sub n and find the limit as n approaches infinity for a sub n. So when we're looking at these different things that we talked about over here, because all of these things are equivalent, we can kind of look at all of these things individually as well. So we're going to look at what we have for each term, and then we're going to look at what that means for our sum overall. So write the expression for a sub n. So a sub n, we're cutting everything in half every time. So 1, it stays the same. So we are going to keep 1 on the top. We have 2, 4, 8, 16. So we have 2 to the power of what we can say n. So what we want to look at is the limit now as n approaches infinity of a sub n. So the limit as n approaches infinity of a sub n, that's the same thing as saying the limit as n approaches infinity of 1 over 2 to the n power. Well, 1 over 2 to a really, really, really large number is that Bobo case. It's going to go to 0. So determine the sum of the infinite series. So we already have some of these values down, so I'm going to rewrite some of the. So the sums for us, these partial sums, are what we're going to use to decide if we are converging or diverging. So we want to look at the partial sums. So S sub 1 was 1/2. If we added those first two terms together, we got 3/4 earlier. We got 7/8, and we got 15/16. So now we need to come up with some equation S sub n. So if we're looking at what we have 1, we have 3, 7, and 15. On the top, and on the bottom we have 2, 4, 8, 16. Well, 2, 4, 8, 16 is the same thing that we had from before, and we know that that was 2 to the n power. So my fraction here for my sum is going to have 2 to the n power in the denominator. The numerators are changing at the same rate, except for we are subtracting 1 from everything. So if I look here, we have 2 minus 1, that's going to give us 1. 4 minus 1 gives us 3. 8 minus 1 gives us 7. 16 minus 1 gives us 15. And we're getting those numbers on the bottom by doing 2 to the n power. So the numerator, we're going to use 2 to the n minus 1 as our numerator. So we have 2 to the n minus 1 over 2 to the n. And this is the function for that partial sum. So now what we're going to do is we're going to take the limit as n approaches infinity of S sub n to kind of help us out to decide if we are going to converge. So we have the limit as n approaches infinity of S sub n minus 1 over 2 to the n. If we do the same thing, we have 2 to the n on top and bottom. These are the things that we want to look at, but they are the exact same type of function. The minus 1 isn't really going to matter that much. And as we are approaching infinity, this is going to be our Eats DC case. We're growing at the same rate, so we're going to divide the coefficients. Well, our coefficients in front are the numbers 2 to the n are being multiplied by, which are 1. And they don't really have anything here, so we have 2 to the n divided by 2 to the n, which is 1. So we are converging here to a value of 1, which means S in this case is equal to 1. Some of the nice things about this in particular is a lot of times they'll give you the equation. They won't necessarily give you a sequence, but they could. The reason why we look at sequences individually first is just to kind of help us understand where these things are coming from. We can always write out a sequence, and we may have to write out a sequence, but we'll look at that when we need to. Okay, so we're going to look at the summation from n equals 1 to infinity of 25 times 4/5 to the n power. So we want to look for if it will converge or not. And in order to decide that, we need to look at those partial sums again. So we're going to look at S sub 1 first. So S sub 1 is plugging in 1 for n, finding that first term. So because we start at n equals 1, we're going to plug in 1. So we have 25 times 4/5 to the first power. This is 25 times 4/5. 25 divided by 5 times 4, which will give us 20. S sub 2, we have that first term of 20 plus our second term, which would be plugging in 2. So we have 25 times 4/5 to the second power. This is going to be 25 divided by 5 divided by another 5 times 4 squared. So we have 20 plus 16. 20 plus 16 is 36. From here is where we're going to want a calculator, because we now have 36, the previous term, plus our next term. So 25 times 4/5 to the third. So each time we're taking that previous sum and adding that next term to it to find our next partial sum. 25 times 4/5 to the third is going to be 12.8. So we're going to be adding 36 and 12.8. So 48.8. And then we would do the next one. So our previous terms sum is 48.8. So we're going to take 48.8 and add the next term. So 25 times 4/5 to the 4th. I'm going to give this to you already. This is 59.04. And then we're looking at S to the 5th, 67.232. S to the 6th, which is equal to 73.7856. So, things that we want to look for when we're looking at this is, if we look at the difference between 20 and 73.78, they're not that close like it was with 1/2 and 1, but we don't necessarily need them to be close. So what we're really looking at is the difference between these values. So the difference between 20 and 36 is 16. The difference between 36 and 48.8 is 12.8. The difference between 48.8 and 59.04 is 10.24. So as we go along, this value right here, what we're adding to it the next time, is getting smaller and smaller. So eventually, if it keeps following that pattern, it's going to be going towards a value that is so small that it's pretty much 0. So looking at what we have, do we think it'll converge? The answer is yes, because those values that we're changing by are getting smaller and smaller. So this series will converge, but it is special. So this is what we call a geometric sequence or a geometric series, depending on if you're looking at the sum or not. And you may be thinking, I saw geometric just a second ago, and you're right, that is what we're going to talk about next.